Now we're ready to talk about RC circuits. RC stands for resistor capacitor. So these are circuits that have both resistors and capacitors in them. Take, for example, this circuit. We have a battery with an EMF attached to a resistor, a capacitor, and right now the circuit is an open circuit. It's not closed, so nothing is really going to happen. The battery is not applying a potential difference across either the resistor or the capacitor because there's no completed circuit yet. The question is, what will happen when we do complete the circuit? Well, if you think about what a capacitor is two plates of metal separated by a gap between them, an insulating gap. So current cannot flow from one side of the conductor to the other. On the other hand, until this circuit is closed, there's not going to be any charge on this capacitor. There's nothing to charge it. It takes a battery or some other supply of voltage to build up a charge on this capacitor. So this capacitor is completely uncharged, and what that means is it's not yet creating any kind of electric field. So if I connect, if I close the switch, allowing current to start to flow, at the very beginning, the capacitor is not going to resist that current at all because the capacitor itself isn't charged. If we think about what the battery is going to do, the battery in a circuit serves to push charges through the circuit. Here I've drawn some charges. I'm going to represent negative charges as blue and positive charges as red. I've opened my circuit again, so nothing is charged. There's no voltage across anything. And if I close the circuit, what's going to happen is now the battery creates an electric field that moves charges around the circuit. The negative charges are the things that are actually moving, right? It's the electrons that are moving. And since we know that the conventional current is going to move this way across the battery, right? It goes from the low potential to the high potential side. That tells us that the electrons are going to move the opposite direction through our circuit. So once we've closed the circuit, the negative charge is going to be pushed from one side of the circuit all the way down, right? The charges are going to be pushed in this direction. Now, every time this happens, every time an electron is moved off of this bottom plate, it leaves behind a positive charge. And as this continues to happen, it's going to result in a buildup of negative charges along one side of the capacitor and a corresponding buildup of positive charges on the other capacitor plate. Now, this is going to keep happening until the positive charge left over here is so strong that the battery is not strong enough to pull any more electrons away from it. And that's when, in this kind of circuit, current will stop. So when the switch is first opened, current will flow effortlessly because there's no charge separation here yet. So the charges are simply going to flow according to the EMF of the battery. But the more charges move, the more current flows, the more the capacitor is going to resist any future current. And as a result, we find that as time goes on, the current is actually going to decrease. And in fact, it's going to continue to decrease until the current reaches zero. And that happens when the voltage across the capacitor is equal to the voltage supplied by the battery, right? Because voltage is a measure of how strongly the battery pushes charges. And when the capacitor becomes charged up enough in order to push charges just as strongly, they'll kind of be stuck, right? They'll experience equal and opposite forces, one from the field of the capacitor and one from the field generated by the battery. Now, since the charge builds up over time on the capacitor, and since the voltage of a capacitor is equal to, crap, what is it again? I always forget this. It's equal to the charge on the capacitor divided by its capacitance. That implies that the voltage actually increases over time. So the capacitor is being charged up over time from the current created by the battery. But the more charged the capacitor becomes, the smaller the current is because the capacitor fights the current. And so the voltage is going to increase over time, but is going to increase slower and slower over time. Meanwhile, if we think about the voltage across the resistor, so voltage across the resistor is equal to I times R. Well, we already established that the current starts out strong. In fact, it starts out as if there was nothing here. The capacitor doesn't do anything when it has no charge. And so the resistor, at first, will basically think it's the only thing in the circuit. It will just be a battery connected to a resistor. But as the capacitor becomes increasingly charged and its voltage goes up, the current in the circuit is reduced, and that reduces the voltage through the resistor. And eventually, when the capacitor becomes fully charged, when it's strong enough to completely oppose any current from the battery, then the resistor will have no current running through it, and now there will be no voltage across the resistor. Now let's analyze this more mathematically. Actually, we still need to look at this. We can do this using the very rules that we've just been talking about with resistors. We can do this simply by using the loop rule. So if we apply the loop rule to this simple RC circuit, well, we have the EMF of the battery. So here I'm choosing to go in the circle the loop in the direction of the conventional current. So I have the positive EMF from the battery. Then I have to subtract, oops, I don't want that to be green. Then I subtract the voltage of the capacitor, and I subtract the voltage of the resistor. You might ask, how do I know I subtract the voltage of the capacitor, right? Because, with the resistor, we know that the voltage goes down if you go across it in the same direction as conventional current. But really all that's saying is we know that this end of the battery, of the resistor, is held at a higher potential than this end of the resistor. Well, that's pretty clear to be the case with the capacitor as well, because this side of our capacitor is left with excess positive charges, and the top side has excess negative charges, and so the bottom side is also at higher potential than the top side. And so as we go around this counterclockwise, we're going from the high potential to the low potential side, so our potential goes down, and so delta V, and we leave out the delta, is negative. It turns out that this is really all we need to rigorously examine the behavior of this circuit. So one thing we do need to add is we know what current means, right? If I look at this loop rule expression, I can rewrite it a little bit. I know that the voltage of the capacitor is Q over C. And I also know that the voltage of the resistor is I times R, and that's equal to 0. But we also know that I is equal to the rate of change or of charge through part of our circuit over time, right? It's the flow of charge through our circuit. So we can now rewrite this expression as the EMF minus Q over C minus the derivative of Q with respect to time times R is equal to 0. This is a differential equation. We've seen things kind of like this before with terminal velocity, drag in general, and a couple of other examples throughout the year. So we're going to solve this in more or less the same kind of way. Let's move it over here. So this differential equation, the two variables in question are charge and time. And the way that we approach solving differential equations is usually, and it works in this case, is to separate out our variables. So that's what I'm going to do. We're going to do a little bit of algebra, and we're going to rearrange this so that all of the expressions of charge are on one side of the expression, and all of the expressions of time are on the other side of the expression, of the equation. And we can do that by writing this as epsilon minus q over c is equal to r times dq dt. A little bit more algebra. I'm going to multiply both sides by dt, so we get epsilon minus q over c times dt is equal to dq times r. And now I can easily rearrange this, so I simply have on the left-hand side dt, and the right-hand side becomes dq, or let's just write this as r dq, divided by epsilon minus q over c. The next step is to integrate both sides of this equation. So I can do that. And I have to set bounds because I want to actually know how this thing is evolving over time. And so I'm going to start counting my time from 0, where that's when I open my circuit in the first, or close my circuit in the first place. And I want to know, what are things going to look like after some amount of time t? Now, when I first close my circuit, the amount of charge on my circuit is 0. And after some arbitrary amount of time has passed, the amount of charge on my circuit is going to become q. I'm going to rearrange the right-hand side of this equation just a little bit, where all I've done is I basically multiplied the numerator and the denominator by the capacitance. This is just a cleaner way of writing this. At this point, I would like you to pause the video and actually complete the rest of this integration on your own. I think it's a valuable exercise. So what I want you to do is I want you to evaluate both sides of this integral, and I want you to come up with an expression for q as a function of time. So if I wait 1 second, how much charge will there be on the capacitor? As a function of the resistor in the circuit, the EMF provided by the battery, and the capacitance of the capacitor. Once you have the charge as a function of time, you should also be able to quickly find the voltage across the capacitor as a function of time. And once you've found the voltage of the capacitor, you should also be able to figure out what the voltage of the resistor is as a function of time. And I'll give you a hint for that one. For this one, you can make use of the loop rule, where we know that the sum of voltages around our circuit has to always be equal to 0. And the battery is always going to provide a fixed voltage. And so that means the voltage of the capacitor plus the voltage across the resistor always have to sum up to the voltage across the battery. So again, pause the video, try to compute these 3 things, and when you're done, come back and I'll walk you through it in case you got stuck, or just to make sure that you did it right. Evaluating the integral on the left-hand side is pretty easy. It gives us t minus 0. But in order to evaluate the integral on the right-hand side, we've got to do a little bit of work. Luckily, good old u substitution is enough here. So if we set the denominator equal to u, then du dq is simply equal to minus 1. And that makes the right-hand side of our expression rc, because the RC term is a constant, it comes right out of the integral, times the integral of minus du divided by u. Evaluating this further gives us t is equal to RC, The integral of 1 over u is the natural log of u, and we have a negative sign out front, so this becomes the natural log of u. But if we substitute back in for u, and we put our bounds back in, because we're integrating from 0 to q, then this becomes negative RC times the natural log of C times epsilon minus Q, evaluated from 0 to Q. Expanding this out further gives us that T is equal to negative RC times the natural log of C epsilon minus Q minus the natural log of C epsilon. We can use our log identities to rewrite this as minus RC times the natural log of the ratio of C epsilon minus Q over C E. I don't know why I said epsilon there. This is just a fancy E. And at this point, we can take this negative sign. We can move it over to the other side. And in fact, we can do the same thing with the RC. So again, a little bit more simplification, and we end up with negative T over RC is equal to the natural log of 1 minus Q over C times E. What we're looking for, though, is Q as a function of time. So we actually have to isolate Q. So to do that, we raise, or we exponentiate both sides. And e to the natural log, simply get the natural log is the inverse of e, and so the right-hand side becomes 1 minus q over c times e. And rearranging that one more step gives us that the charge as a function of time is equal to the capacitance times the EMF of the battery times 1 minus e to the minus t over RC. And this is the first of the equations that we were looking for. We can really easily get to the voltage of the capacitor over time because the voltage is simply equal to the charge divided by the capacitance. And so the voltage of the capacitor is simply the EMF of the battery times 1 minus e to the minus t over RC. We'll get to the behavior of the resistor in a bit, but first I want to stop here and I want to talk about the behavior of the capacitor. So the first thing that we should do is we should talk about what is happening at t equals 0. Well, when t is equal to 0, then e to the minus t over RC is equal to e to the 0, and that's just equal to 1. And if that's equal to 1, then q is equal to 0. And if q is equal to 0, then the voltage of the capacitor is also equal to 0. And as time increases, e to the minus t over RC becomes e to the negative of a bigger and bigger number, and that means this term is getting smaller and smaller. So we're subtracting a smaller value from 1 here, and so as time goes up, q and v both go up. So now let's consider the other limiting case. What happens as time approaches infinity? Well, as t approaches infinity, e to the minus t over RC approaches 0. Recall that e to the negative t over RC can always be thought of as 1 over e to the t over RC. And I think it's pretty clear that as t gets big, this gets really big, right? It's an exponential. And so 1 over a really big number becomes increasingly small. Now, if this goes to 0, then that means that as t goes to infinity, the amount of charge on the capacitor approaches C times epsilon, and the voltage of the capacitor simply approaches the voltage of the battery. What we're seeing here is actually that the voltage across the capacitor never actually reaches the voltage of the battery. It only asymptotically approaches it. Now, it happens very fast because this is an exponential function. After after certain amounts of time, it becomes almost impossible, or eventually even impossible, to tell the difference. But technically speaking, the voltage never quite reaches the voltage of the battery, and the charge never quite reaches this value, and as a result, the current never quite reaches zero. There's one other value of time that's worth looking at, and that's at the value of time t equals RC. Note that the units of R times C has units of time. You can see that because if you work it out using SI units, the units of ohms times capacitance times farads has units of time. But also, I mean, if we just look at this expression, right, T divided by RC has to be dimensionless because I can't have a dimension-full quantity inside my exponential. Or if we look back to where it came from, you can see the comparison here as well. You can match units to see that they in fact have to work out. Right here is the easiest place. du over u is a dimensionless quantity, and so here we have t is equal to units of RC. All right. So at this special case of t equal to RC, we have that the charge is equal to C times E times 1 minus the exponential of e to the minus 1, which is C times E times 1 minus 1 over the number e. If you calculate what this is, we find that it's equal to about 0.63 times C times the voltage of the battery. Or the voltage of the capacitor at this value of time becomes about 0.63 times the EMF of the battery. RC, because it's a sort of a characteristic time, it's a quantity that has units of time that simply shows up in our equation, and it depends on the properties of our circuit. And so it's a property of the circuit that gives us the characteristic time behavior of the circuit. And so we actually give it a name. We literally call it the time constant. And we label it with the Greek letter tau, and it's simply equal to RC. Note that if RC is very large, if the time constant is very large, then it's going to take a long time for the voltage of the capacitor to become almost 2/3 the voltage of the battery. The larger the time constant, the longer it takes our capacitor to charge up, and the longer current will flow meaningfully through our circuit. If our time constant has a small value, then the voltage will very quickly of the capacitor will very quickly approach the voltage of the battery, and things will come to equilibrium much faster. So it depends on the product of R and C. If R and C are both very large, then our circuit will take quite a long time to come to equilibrium. But if their product is small, then the circuit will come to equilibrium where the current stops flowing rapidly. Now we can analyze the behavior of the resistor. So if we go back to our loop rule, we know that the EMF of the battery is minus the voltage of the capacitor minus the voltage of the resistor has to be equal to 0. And so we find that the voltage of the resistor is equal to the EMF of the battery minus the voltage of the capacitor. And the voltage of the resistor is then equal to the EMF of the battery minus e to the minus t over, I'm just going to write this as tau. I'm going to use our time constant symbol. And we can see that these two, right, this is going to be the EMF minus the EMF plus this. And so the voltage across the resistor is going to be equal to e to the minus t over tau. And this decreases over time, right? Because as t gets bigger, this exponential term, this becomes a bigger negative number, so this becomes 1 over e to a bigger number. So as time goes on, the voltage of the battery, oh, I'm sorry, there should be EMF of the battery right there. So as time goes on, or as when time is 0, this exponential term is just equal to 1, and the voltage of the resistor is simply the EMF of the battery. And that's because at first the capacitor does nothing, so current will flow through the circuit with the only thing resisting it being this resistor, and so all of the voltage of the battery falls across the resistor. But as time goes on and the capacitor opposes the current more and more, smaller current flows through R, and the voltage across the resistor approaches 0. Now let's talk about the current through the circuit. Well, we know that I is equal to dq dt. But we also found that that q, as a function of time, is equal to c times the EMF of the battery times 1 minus e to the minus t over tau. Again, you should pause the video and you should complete this derivative. And when you've done, come back and check to see you got it right. So this derivative comes out to, the derivative of this first term is just c times epsilon naught, or not epsilon naught, c times the EMF. That's constant, so the first term goes away. So all we care about is this. So we have the derivative of c times e times negative e to the minus t over tau. And when you compute that integral, you get c times the EMF of the battery divided by tau times e to the minus t over tau. Note that the negative sign went away. In reality, there's still a negative sign, but then we bring down a negative tau when we do this derivative. This comes from the chain rule. And tau is equal to r times c. So we can erase tau. We can rewrite that as minus rc. And we see that the capacitances cancel out, as do the signs. And we are left with the current as a function of time is equal to the EMF of the battery divided by the resistance of the rest of the circuit times e to the minus t over the time constant. And again, we can note that as time goes up, e to the minus t over tau implies that the current goes down and it approaches 0 as time approaches infinity. So next, let's graph what this will all look like. So I'm not going to graph every one of the functions, but I do want to specifically talk about the voltage of the capacitor and the current through our circuit. So first of all, we know that when t is equal to 0, this exponential term just becomes a positive 1. And so when t is equal to 0, the voltage of the capacitor is 0. On the other hand, as t approaches infinity, this term approaches 0 because it's 1 over e to the t over rc, and as t gets bigger, e to the t over rc gets bigger, and so we have 1 over a bigger and bigger number, and so this becomes 1 minus something approaching 0. Over time, the voltage of the capacitor simply approaches the voltage of the battery, but it's an asymptote. And so if we graph this, it will look something like that. Now, there's one other point that we can label. We can label that we know exactly when the voltage of the capacitor is equal to 0.63 times the EMF of the battery. This occurs at the time constant RC. We can do the same thing for the current now, and we know that when t is equal to 0, e to the minus t over tau is just equal to 1, and so that means that our current starts out with a value of E over R, and that's just what the current would be if there were no capacitor in the circuit. But as t gets bigger and bigger, this term approaches 0, just like it did over there, and so the current asymptotes from E over R to 0. The last thing I want to talk about is discharging a capacitor. What I mean by that is, let's say I have a capacitor that's already been charged. I've hooked it up to a battery, it's been charged up, and now I want to get rid of all of the charge that's on it. If I just leave the capacitor disconnected from anything, sitting there for a long time, it will eventually leak charge into the environment around it, but depending on the capacitor in the environment, that could take a very long time. It could take decades or even longer. So what if I want to get rid of the charge right now? The easiest way to do that is to hook it up to a resistor. What will happen now is that all the positive charge clumped up here and all the negative charge clumped up on the other plate, well, now they have a route to recombine with each other. So the electrons over here are no longer stuck. They can easily just move through the circuit until the charge is balanced again and our capacitor has no more charge separation. In this circuit, the voltage of the capacitor has to be equal to the voltage across the resistor. And we can use this fact to analyze how the voltage across the capacitor and across the resistor is going to change, how long it'll take for the capacitor to discharge. And we can do that by saying we know that the voltage across the capacitor is Q divided by C, and the voltage across the resistor is equal to the current times the resistance. And we know that the current is equal to minus dq dt. And this minus sign is important, and it's not obvious. Ooh, Pablo's gone crazy. The minus sign is important, but it's not obvious where it comes from. And it comes from the fact that the charge on this capacitor is decreasing over time. So Q is decreasing. That means dq dt is negative. But when I talk about I here, I'm talking about the magnitude of the current, because I know that the voltage across the resistor, the way I've written it, needs to be positive. The left-hand side is positive, so the right-hand side needs to be positive, and that means I need a negative sign right here. We can finish analyzing this equation the same way we derived the behavior of the charge of the capacitor in the previous example. I just want to separate all my variables, and so I can write this as dt is equal to negative dq over q times RC. And once again, I can integrate both sides. I'm going to start at time t equals 0, which is when I connect the circuit to start discharging the capacitor. And when I integrate the right-hand side, this time I'm not starting with 0 charge. This time, I start with whatever the initial charge on my capacitor was. And I end up at some arbitrary value of time with whatever the current charge on my capacitor is. So the bounds of integration are actually different this time. And the integral is very similar, although this time it's much easier. This integral clearly just becomes a log. RC is just a constant, and so we can solve on the left-hand side. We have t. Oops. On the left-hand side, we have the time, and on the right-hand side, we have negative RC times the natural log of Q, evaluated between its initial charge and its final charge. We can rearrange this the same way we arranged the example before. I want to solve for Q as a function of time, so we can again write this as minus t over RC is equal to the natural log of Q divided by the initial charge. We can exponentiate both sides, and we get that the charge as a function of time is equal to the initial value of charge times e to the minus t over RC. And if that's the charge, then the voltage, what happened? Oh, then the voltage across our capacitor is simply Q naught over the capacitance times e to the minus t over RC. This is really just kind of like the inverse of what we just did. For example, if I graph this, I start out with simply the initial voltage of the capacitor, which is Q naught over C. And as time goes on, that asymptotes to 0. Whereas in the previous example that we had before, it was the opposite. We started out with 0 voltage and it asymptoted to some final voltage. So the behavior is basically just reversed. So now let's talk about the current through the circuit. Again, we can analyze this the same way as we did before. We know that the current is equal to the rate of change of charge over time, or the flow of charge over time. And we know what the equation for charge is. It's right up here on the left. So we can just take the derivative of that. And when you complete that, we find that this is simply equal to Q naught divided by RC times e to the minus t over RC. Where again, RC can be written as our time constant tau. And this quantity here is simply the initial current that will flow through our circuit. And so if we graph this one, we start out with some initial value of current, I naught. And again, just like our graph on the left, the current decreases over time. Now this is a little bit different than our previous example. In our previous example, the behavior of the current and the voltage across the capacitor were kind of different. We started out with a circuit where we had an initial current and it decreased to 0, and at the same time the voltage across the capacitor was ramping up. Now we have a different scenario because the current is doing essentially the same thing. We start out with an initial current and it approaches 0, but this time the voltage is also ramping down. And the reason for that is in the initial circuit we had a battery, and that battery was responsible for the initial current, but it was also responsible for charging up the capacitor, which eventually stopped the current. This time there's no battery in our circuit, and it results in the capacitor playing the role of the battery initially, but as it discharges, it basically becomes a weaker and weaker battery, and that implies that we have a smaller and smaller current. And that's all for now. See you next time. Oh wait, first, blooper reel. Okay, Pablo, that's enough.